Hello, and welcome to the Lightning Talk seminar, How PC Intros Are Made. For this seminar, we have a list of 6 talks, so I invited 6 of the best PC intro developers, and so we will start with NuSan, and then you can see the list with NR4, Prost, Zavie, Cédric, and Psycho. So we have quite a lot of content, so we will try to go quickly. If you have questions, we will take them at the end, so after all the talks. And yeah, so there's quite a lot of content in the slides, so you can look at the QR code if you want to access them. And these slides will be again at the end of the conference, so if you need access to the links later, you will be able to find them. So first, we will start with NuSan.
Hello. So I'm NuSan, and yeah, I will talk about path tracing and an infinite amount of primitive, but fake. So I made a few PC4K intro in recent years, and those 4 of them are using real-time path tracing. And who has already made some patch tracing in the past, or some other global elimination stuff? Yeah, a few people. So I will talk a little bit about path tracing. So the goal is to make light bounce around and to get some kind of global elimination. And usually you use ray tracing to cast rays from the camera to the surface, and each time it hits a surface, it will bounce around in a random direction. And that will depend on your material properties, so roughness, transparency, or other stuff. And at the end, it should hit a light, and then you know how to calculate your points. The issue, path tracing is pretty cool for 4K because it's not much code. You can see it's pretty simple. It's easy to implement. You just make things bounce around. But it's also very slow and very noisy. You can see here, with 100 samples per pixel, you still have a lot of noise, and it decreases very slowly. You also get for free with path tracing some anti-aliasing, some high-quality depth of field, some motion blur, and basically you just randomize what you want to blur, the pixel, or the camera location, or the time, and the path tracing will average things around and do things for you. The only missing piece you can't really have like that is bloom that you have to add in post-process. You could use ray marching for your path tracing to find the next surface, but ray marching needs at least 30 to 60 steps to be any useful. And if you multiply that by like 20 samples per pixels, it quickly gets very slow and still very noisy. Except some very simple scenes, like a few cube and spheres, it's very much too slow for real-time uses. And one solution I found is to use analytical ray tracing. So basically you skip the ray marching loop, and you want to know directly what's the point you are colliding with the primitive. And some simple primitives like spheres, boxes, cylinders, capsules, you can compute it analytically just with the position of the ray, the direction, and your primitive. You can get the collision point immediately. So it's super fast, but now the computation costs grow with the complexity of your scene. The more sphere or boxes you have, the more costly you have for your scenes. And you also cannot use the tricks of domain repetition that you often find in ray marching. You cannot do infinite repetition scenes. Or can you? where with some limited stuff, you can repeat it some primitive around and get more details than what you're computing for. So I will give you an example. Here is an octahedron with path tracing, and you can carve a box from it. And this is computed analytically. And you can see here where the box is. And the basic principle is that you will, when you first intersect the octahedron, you slice the octahedron into sections. And basically what you will do is that you will carve a single box, but depending on the section, you will move the box around. So you get the box in each of the sections. And so you now have a lot more details than what you're computing. This is still just one octahedron and one box test. And you can also change the parameters, like making more or less subdivision depending on where you hit the octahedron. And you can add motion or things like that. And with only that, you can do a scene like that. And this is just 2 octahedron tests, 3 boxes, and 1 plane. So you can do a lot more samples, like here it's probably 20 to 30 samples, and you start to get all the good things about the lighting. This is the same scene with the same few primitive tests, and this is also the same thing. This is 1 cylinder and 2 boxes. This is the same cylinder and 2 boxes, so you can find some variety. 10 spheres and 1 plane. This is 10 spheres, 3 cubes, and 1 plane that moves around. And this is the same, and this is 2. So you can really go beyond the usual 2 or 3 primitives you have with analytical raycasting. And in conclusion, there is still a lot more to explore in that, with that stuff. And it can be tricky to handle all the special cases, but pretty often you can cover the artifacts and get away with it. So in conclusion, get more out of your primitives. Thanks.
And next, we have NR4.
Hello. Okay. Good afternoon, everyone. I have prepared some slides on color gradients, and I hope you're interested in that as well. First of all, and thank God the projector is nice, I can show what I want to show. We have I want to define first what I mean by gradient, and this is specifically a list of colors with weights assigned, and those colors are interpolated then smoothly to get a color gradient. And this 2 examples are shown on the slide here. The left one is smooth, and in the right one you immediately notice that there is some kind of lightness differences, especially in the red part of the image, and where you can clearly see something is going on and is not being smooth. And I can, so to say, I looked into what makes a good gradient by some definition that I present to you now a little bit more, and this is slowly changing lightness makes usually a nice impression on your brain, and also if you specify a set of colors and compute a gradient over it, then you expect that only the colors you specify are in the gradient, and those both 2 properties of gradients are shown below. Where you can see is a color gradient mixed in two different color spaces. In the first color space, called O club, whatever that is, there's no lightness difference, and in the space directly under it, HS3, which you might know, there are visible stripes, and those are from those gradients. From the low gradient, there is a lightness gradient displayed on the lowest stripe, where you can exactly see what I mean by those stripes. And on the right side, there is an example of the wrong color being in the gradient, where you have the left of the two gradients has only white and blue, and the right one has also some purple, which in this case is not wanted. And how can we achieve this? That we have a good gradient with not that many stripes. The first thing we have to do is weighting it. Without the weights, we won't be able to achieve anything good at all. Which means if colors are very different, that they should have a longer distance between them in the gradient. And this, of course, means in a color space. And also, we don't take just the color space our internet memes are being sent around in as RGBs, but we look into what color spaces are available and pick one that suits our gradient best. And also, because we're size coders, we want to pack this into as few bytes as possible. So we also want to have some kind of math that produces the gradient, which I will call color map. And you see on the bottom, this is the same colors, but with different weights. And the weights are indicated by the small notches on the bottom of the color gradient. Yeah, and as you can see, the color gradients are very different depending on those. And so what's with the color spaces? Yeah, okay, I have 10 minutes. I can tell something about color spaces, sorry. But there are many of them, and there are conversions between them, and some of them are more lossy, and some of them are less lossy. And in principle, it's a graph theory thing. You mark in a graph where which edges do I have that are the transformations between the color spaces, and what color space is the image in that you use as input. Then you identify where you want to do your computations. You apply all transformations that are on the way to there, potentially minimizing the loss on the way of color information, and then you transform it, you do your computation, you transform it back, and you receive a very pretty gradient. So much for the plan. Yeah, and how to pack this into an intro. Yeah, there was a smart idea that IQ had once. He used a specific model with a cosine, and some of you might have already seen this. This is on the right side, and this is used widely on ShaderToy. But as you can already see, some of them have some of the lightness stripes I was referring to earlier. And yeah, I created a different model for this. I use polynomials in Horner form. They are written down there, if you're interested. They can do the same thing, but they can potentially have more parameters. And they work a little bit better to remove those lightness stripes. And now, how do we get those parameters to pack this tightly? Well, we have to use some kind of optimization technique, and for example, Levenberg-Marquardt algorithm. This is usually what packages, software packages do. Optimizers that won't tell you what they do, but other optimizers will tell you, and there are tons of optimizations algorithms like this. Yes. Yeah, and on the right side you can see some of my gradients on the lower right side. Yeah, for the people who don't want to write the code for this because it's somehow a bit of overhead, I wrote a tool and it's published, and I want to show it real quick. If I manage. So, tool is this one. And as you can see, you have an image in the center. And you can drag and drop images from somewhere else into it. And I assume we will now want to rip colors from this one. Now I can drag my cursor around in it. It acts like a regular color picker, hence the name. Then I can start to pick colors from it. Okay, this is harder than I anticipated, but we will manage. Yes. Yeah, the process is a bit slow now. Sorry for that. This one, maybe. This is a bit awkwardly pink, less pink. So, now we have a decent gradient, and of course, we want to have it in our intro, so we press Ctrl-C, and the next step is selecting selecting a shader for it, and this would be, 1 second, can you hold this? Thanks. Paste it directly into your code. You paste it directly into your code, which has worked here. I can show this. And as you can see, the parameters are there. And if we're super brave, we drag the command line window there as well and show that it works. We were too brave. Sorry, this is on the wrong screen now. And we have the color gradient. So, and this is the tool. And I actually prepared a release to release after this talk. So if you're interested in the tool, you can download it here. It has some more features, but I won't detail them here. You can check it out or talk to me afterwards. And I hope it is useful to you. Thank you.
Okay, thank you. And next, and then welcome to Pro of Nuance. Here's the mic.
Thank you very much. So, how PC intros are made is the title of this lightning talks, and I thought it's a good idea to just give you a little bit of a making of how we actually did our intro XO that we released last year at Evoke. Now, XO is a 4K intro, and it's about a monster that wakes up in a post-apocalyptic city, strolling around, enjoying it somehow, but starts to consume it, enjoy the whole city, crave for more, and finally reach for the stars. So actually, was that the story that we had, like the idea that we had in the beginning, and we said like, okay, that's the story, let's make an intro? Actually, no, that's not how it worked out. So when I try to do like an intro or a demo, I always try to find some kind of technology that I find interesting, and then I just find a story that actually allows us to communicate the technology. So the technology produces a story. So this is how we ended up with XO. And so what's the technology in XO that we actually wanted to do? it's the animation and the walk cycle, because this is someone that I rarely saw in intro in the last years, and I thought, okay, let's try it out. Now, there was a Houdini challenge a few years ago where people tried to create procedural walk cycles of monsters, and they were doing like very complex setups. And I was looking at that a little bit. It was a really fun challenge to see what people were coming up with. But it all, like when you break it down, it's all about just one thing, and it's contact points. So this means the monster has to step onto the ground at some time. So let's see if that works, because we have a video for that. So what we do is we simply spread a bunch of points just like on that line and move the body around and just build a constraint and connect the body to the closest points. And that's basically it. So you already have like some kind of 2D walk cycle. Now, if you want to do that in 3D and you want to ray mesh that, it's actually quite expensive to calculate all of that. But it's a very, very simple trick. Simply still calculate it in 2D. What you do is you just fake the points on the 2D plane, and then you just connect a few lines together with a sphere with a nice SDF and render that. And you already have some kind of a monster walking around. But the thing is, it looks creepy, yes, but is it like a huge monster walking around? It's actually not, but so there's the next video now on that runway. It's a great work in progress video from back then. Now, what I did is here, I used the progression, so the distance basically from the head to the ground, and used that in the pulse function to give it a lot of more energy, so it's like you can communicate the weight of that monster. And what I also did is I just put a little bit of a sign stuff on the progression, and yeah, with a lot of tweaking, it actually ended up like it looks now. So the thing is, just having that guy walking in an empty field didn't look really good. So fortunately, there are those crazy guys on ShaderToy, Lee and Uxor, and really mad props to them, because they built this crazy city fractal that I used quite a few times already, and it's really, really nice because it just creates these great cities. So what I did, I just carved out a long street, put a guy in there, and it looked really, really, really good. But then there was the next problem. I have a guy walking through a city, and I have absolutely no fucking idea what to do with that guy. So that was a big problem, and it kept me busy for 3 weeks, I guess. So I was just sitting in front of my computer watching the guy. It was really funny to watch the guy, but I had absolutely no idea what to do. So I was researching a lot, looking around, like, what could I do? Like, I mean, sure, in the end, it was pretty obvious that the guy would destroy a city, because I came across this crazy movie poster, and that's a slogan that we really love, right? And yeah, it was Godzilla, and this kind of sold me. So I was looking into that, like all those movies and the franchise, and like what to do. And at that time, EXO looked like that. It was actually a colored intro. But I tried around, tried a few things, never worked out like I wanted it to look. So I was looking a little bit more into that Godzilla thing, because I'm actually didn't know all of those movies. So I was looking at the very first movies, and I found that. Yeah, and that sold me, because the colors were just great, like this black and white, that depth behind that, the crazy good typography, something that you can do in the 4K with a few adjustments. So I tried it out, it worked, it fit in the space. So we ended up with our guy, EXO, walking through the city, consuming it. He was shining some light onto that, but he had a job to fulfill and destroy the city. And that's the thing, we all have a job. My next job is I want to release that intro on ShaderToy, so everyone can play around with it, look at how I did the animation stuff. And you know, you never expect what's next. Thank you very much.
Thank you. And next we have Zavie.
Hello. So yeah, Zavie here. So these days I've been evolving our mesh gen, and I'm not finished, but maybe I can share some thoughts with you already. So I'll start quickly with showing to you the evolution of our mesh gen when we started from essentially nothing to where we are today. We wrote more in detail about the some of what I'm going to say. So if you're interested, you can check that link. When we started our first 64K, we didn't realize how much work a 64K was, but we still figured that if we cut some things, we had a better chance of finishing it. So right from the start, we decided to do without any mesh and just have cubes instead and nothing else. And well, you just said have an interesting take and do a story from it. We had a very uninteresting take and did a story from it. But mind you, with just cubes, you can already do a lot. You can stretch and combine them, and you can move individual vertices, and you can already get, something. Next up, we added something called the surfaces of revolution. So think cylinder on steroids. If you use a spline to describe a silhouette, you can do those chess pieces, for example, or the toy figure. And if you have your surface, your cylinder, and you start stretching it or whatever, you can also get some interesting faces, shapes. Like, for example, the chimney in the back is also one of those cylinders, so to speak. And if you have the axis follow another spline, you can get, for example, the mug handle, or you can get the roller coaster train track. And after that, we added various other features. So height maps, face extrusion, smoothing, marching cubes, etc. So this opens up a lot of interesting possibilities. In immersion, we experimented with something. The statue over there in the back is done with marching cubes and a sign distance fields function. And it was not very efficient because it's the only mesh in the entire demo that uses that, so it has to bear all the cost. But I think there is something to explore over there where you can use the expressivity of sign distance functions and the performance of polygon rasterization. So maybe something to do there. After some pictures, here's some code. This is the vertex structure we started with. It has position and a bunch of other stuff. And by the way, the code from our previous intros is available online, so if you want to check it, you can do so, even though I'm going to spend the next few minutes explaining how it's all sorts of wrong. So we started naively drawing the cubes one by one because we didn't know any better at the time, and we quickly realized that was not a good idea because that's killing performance. So we had to put them together into a same buffer, and that's what those functions here do. I don't remember why there are two of them. Maybe that's because we discovered how to use VBO at the time, and that was a bit of a mess. Then we started to stretch our cubes. So this function here appeared, but we still didn't have a mesh at this point. Then finally comes a mesh data structure. So it's very simple. There is no fancy edge stuff or anything like that. And it hasn't fundamentally changed since then. But you can already start to see a problem over here, because in the vertex structure, we have an attribute that's commented. And the reason is because from one demo to the other, we didn't need the same stuff. And as time passes, it gets worse. And here you can see a desperate attempt at managing those different needs. And the problem is we also have an engine library at this point. But we try to have this engine code not specific to the demo, and having to compile it with different flags is not very convenient at all. As for the mesh, it has a lot of features, but it's a little bit of a mess. And the reason is because we didn't understand what we needed. We didn't have enough perspective at that point. I'll give you an example. I was experimenting with the vertex-based ambient occlusion, and all I wanted to do is verify that my AO was working correctly. So I needed to send that to the shader, but I had nowhere to put it in the vertex attribute. I didn't want to add an AO attribute and carve into stone that from now on all the meshes would have AO. So for this proof of concept, I actually put the AO into the texture coordinate because I just wanted to test my thing. But conclusion is the first thing to fix is the data structure. So it's too rigid. Each demo, each mesh even have their own requirements, and we want to be able to define a vertex attribute as needed, essentially, so per mesh. And of course, I want something that's simple, that takes little code, because we're doing size coding. So this is what I came up with. Instead of having an array of vertex attributes, an array of vertex, we have a separate arrays for each of those vertex attributes, and that means if you want to add one or remove one, you can just do that per mesh and without impacting the rest of your code. And since we use positions pretty much all the time, we have a helper for it now, and that shows you how it works. The attribute vertex buffer looks like this. So it's a union simply of all the types of arrays that we have. It's ugly, but it's good enough for us. It's straightforward. It has no overhead for the code. And now, in theory, we should be able to define attributes that we want on a per needed basis. And I say in theory because the code works, but we haven't used it in production yet, so we haven't felt the pain or we haven't gauged how it feels right now. Now, before talking about the other problem that we have, here's a game. It's called Tendis. It's a game in which you are given a few transforms, like that you see here, and you start with a square, and you are to create a certain given shape. So that's essentially a mesh gen disguised as a puzzle game. And as a mesh gen, I think there are two things it does really well. One thing is the UI is pretty clever, and also they are very simple operations, and yet you can create fairly complex shape already. And I was playing this game and I realized, wait, I can do a lot of our revolution shape of revolution can do, but and even more, but with much simpler functions. So I started going back to the revolution function. I'm not done with this yet, but I'll just mention that. So before we had one large piece of code that would generate a mesh from scratch with way too many parameters, and the code to handle all of that was too big, gnarly, brittle, but it worked. And now, instead of that, we have much smaller bricks. So we have one piece of code that generates a grid, transform it, and then other pieces of code that transform it this way, that way. And that gives us a lot more expressivity for less and simpler code. Now, the difficulty is going to be finding the limit between too simple and too complex, because when you think about it, at some point you're like, well, everything is a function. But combined, the two changes that I've just described saved us about 300 bytes, and we have a lot more expressivity than we had before, so I call that a win. Finally, there is one thing I didn't mention about our first intro, is that although it's technically not part of the mesh, we had L systems that we used to place the mesh in the scene and animate them. So I think it's definitely a tool to consider for geometry in general, because it's really simple to implement, and it gives quite some variety already. I don't remember what any of this means, but it doesn't matter because you are the one defining the grammar anyway. It's compact. It's very easy to use. We used it a lot in the first demo. And at the end of the intro, we had some trees, and we didn't want them to look all the same, so we have a bit of variation. But it's still a bit rigid because only the first rule has variation, and I think what we would really want is being able to have variation over all the rules, so you could have something a little bit more abstract. And at this point, I'm wondering if we could describe most of the mesh generator using a grammar a little bit like the L system and have like sort of a super L system on steroids. I don't know, something to explore possibly. The other question I keep coming back to is how to reduce or even remove the distinction between a mesh, a scene, between what is static, what is dynamic. Because this distinction is kind of arbitrary. It's like a technical limitation for, due to hardware or whatever. And it makes the authoring tedious. Sometimes you don't know what you're doing, if it's going to be two separate meshes, two separate scenes. It's annoying. Mr. Vux has a really good model where he regenerates the entirety of his geometry at each frame, and that allows them to do like crazy stuff that you don't see any other demo doing. So I think that's a good area to explore. But more important is the question of how to maximize the expressivity while minimizing the complexity. When you add a feature to your mesh gen or to your procedural generation tool, you can ask yourself, like, if the the expressivity that you gain, how much you gain of that, and then you look at the complexity that you added. Are you going up or are you going down? And if you have something where you increase expressivity while reducing the complexity, you're onto something. As a conclusion, I leave you with this thought. I think procedural mesh generation has a lot of potential yet to explore. That's true for the demo scene, but that's also true in the industry. I suspect it's not very popular because it seems very complex, and it can be really complex, but you don't have to implement complex things to get very interesting results either. So I hope to see more experiments in that direction, and I'll hand it over to Cédric.
Thank you.
Hi everyone, I'm Cédric. So I'm a newcomer to the demo scene. I just started last year with the Equiratus Redentus. So I will talk about the birth of that character, how it's done, and how it's animated. So here is the topics I want to tell about today. A bit of context, the plan, and concerning the pipeline, the model and skinning, the grooming and look dev, the animation, and finally the sequences, how the animation is put into, turned into a movies. So a quick intro. I've been looking at demos for the last 30 years. And I believe I need to do something different to make a demo to exist. So I've been thinking for a very long time what to do and what can be new, what I can show to the scene and exist as a demoscener. I had some ideas around the I-key solver, some kind of a spring motion. I could turn some cubes into jelly and things like that. Maybe I could turn that into into a production. And I wanted to do an animation that runs in 3 minutes with only 64K. So at first, I do plants. I like making plants. So the model would be an SDF because it's really small and it would fit into a 64K. The IK solver would be a set of bones with some constraints between them. So just springs and a bit of angle constraint, but really simple. The hair would be individual meshes that are just like the bones, connected to the surface and moving with some spring. And the action would take place on an island because it's really easy to just put water all around and focus the production and the camera on one tiny bit. And also, yeah, I like making plants, and I wanted to do an animatic, basically some kind of a rose animation in Blender. And I would try to copy some movies, some camera frames from movies, and yeah, try to learn the scenario from that. So the model, I started with Magica CSG. It's a CSG editor with a sign distance field. So basically, you put SDF primitives around, you move them, you set how you want to merge them, if it's union or intersection, etc. It's really easy because you can move the primitives until you get something that looks like what you want. So basically, on one screen, I had a picture of a character, and on the left, I have Magica CSG, and I move and scale the sphere, so it looks at the end something quite like on the picture. It's slow, but you get something at the end. The skeleton is simple, just bone is one node to the other. The skinning is simple as well. It's just per bone. You have some capsules and size, and that would set the influence for the vertices inside that capsule. And I tried to turn that into a pipeline, non-destructive pipeline, so that when I change the sign distance field for the model, for example, I don't break the influences, and it's always recomputed when I start the demo or the tool. So the grooming, same, always the data connected to the bone. So per bone, I have one color, one hair is one UV coordinate on the character, and the entire character is rendered into a texture in UV space. And that's really important, because that way I can produce the texture with every texel is the coordinate, the world coordinate of that textile used in world space. That way I can just set one UV per air, and I can know where that air is in the world. And the animation, that was the fun part. It was at that time that I thought I got something interesting. Just like the pipeline, I wanted to do something that's easy to manipulate and easy to fix. I have a small set of primitives for the mesh, and for the animation, I wanted to only control one root position plus some other parameters, but I didn't want to animate individual bones. So that's the tool, and the only control I have is the root. I can move it all around, and everything is procedurally animated with the spring constraint. So the eyes, it's easy, it's just a look at. For the postures, quite early in the production, I thought that just having the root control was too limited, so I added some postures. It's just a posture is like is just a set of bones, and the position it tends to have. For example, you can have the end, and you want to put it above the head. So just that, just one node and one position. I had some procedural animations as well. That's easy to do, like the breathing. You change the size of one bone with a sign. And the tail animation is just a random force you apply at the end of the tail randomly, and it's just like a mesh movement like that. And that's basically it for the animation. So the rest is just setting parameters and the position of the root. So I did an ImGUI component for that, and I split the whole demo into small sequences. That's the value here. So in the tool, I can just click the sequence I want to edit. The timeline will update, and I just have to put the keyframes and set them timing. So that's a big part of the demo for the character, and the rest was quite simple compared to that. The island is just made of boxes, so I did a quick tool to put boxes, edit their scale and position. Then I've added some static lighting, which is a simple light mapper where I render like 200 frames of the island at different viewpoints, and I accumulate the lighting for that. It's good enough for some occlusion and some simple lighting. Yeah, dog food, that's a term I first learned at doing at my work. Dog food is to use your tools like a lot. Just use it, and if it's broken, fix it until you can do your production with that. As an engineer, I tend to not use my tools because I do them for someone else, like artists. And with that demo, I try to use it as much as possible. And I could make it quite stable, so it was great. It was great doing your tool. I will definitely do it again. And yeah, that's it for me.
Thank you. And finally, we have a talk by Psycho.
Yeah, this is about how you do the scripting, the timing in your intros. I think many are still using hard-coded scripting in the shader. But I think it's better to have some level of tooling at least, even in a 4K. So this is how we're doing it. We're not going to release our framework, so this is more inspirational. We're using the system called GNU Rocket, mostly made by Kusma through the many years. Personally, we prefer the Emun's editor, as you can see. So it's editor part, and then the library you integrate in your system, and then the communicator over TCP. So essentially, you have a lot of tracks for different values, and then you can interpolate different interpolation methods and so on for every track through the demo. So yeah, that's camera angles, what objects do you have, where are they, fading, and so on. So why are you using a tool? Why are you using a sync tracker instead of hard coding it? I think the primary advantage is the instant feedback you get. You can move values up and down and see the result immediately. You can also have the timelining, so you can step both forward and backward in time. You don't have to start the intro all over again and again. And finally, you can give the tool to someone else, so the graphics artist can adjust the colors, or someone can do basically everything in the intro. You can do without it, and it might be smaller without it, but I tend to say that you will get better result by having these things because you have more iterations, because iterations are easier. Then maybe a bit provocative. What is actually a good 4K intro? I think it's a single effect, a single technical concept, and then you adjust some parameters to make it look like 10 effects or whatever. So that should be a perfect use for something that can interpolate variables through a demo. We did our Rocket integration when we did Nexus 8 many years ago. It's a more than 6-minute demo we had to recreate frame by frame, more or less. So it was obvious to get something better than the hard-coded stuff we had before. So we had these 28 tracks in this case, controlling everything. We can step forward and backward, and we even had, in this particular case, we even had this video window of the original demo. So that was synchronized, so we could step forward and backward, get the text to slide in at just the right way and time and so on. It really proved itself in this particular one. Then you will say, you can't have that in a 4K. Yes, sometimes it is too much. We have had intros where we only use the timelining, not really using the system, and sometimes it makes sense just to hard code everything if you have some concept that works for it. But our replayer is really small. It's 135 bytes. It's full featured. And we have all the variables, you can have proper quantization, not just some random number in your shader that may have a different form every time and so on. We get float inputs, so you don't have these large constants all over your shader. Everything will just be pretty clean, and cleanness is a good thing for compression. You're doing things in one way and not doing each effect in a new way that will compress worse. This format we have is really cheap for extra channels. It's a few bytes for an extra channel. So even adding one a variable you will only change once or twice, that's no problem. And then you will have the instant feedback when editing it. So how do we do it? The most important thing is to quantize your values. And it's important that you also do that when you are in editing mode. So you can see that this change didn't give a change in the actual demo, where you have to change a bit more to get to a new quantized value. So we have, for each channel, we have a quantization factor, which we will adjust in the final phases. We have our own export function, outputting a sampler with a lot of labels and so on. So we have some good overview in the Crinkler report. And this exporter will also do some of the manual work of quantizing, where it's not meaning anything and removing keys that you don't need and so on. And then we have our separate replayer that is, it's really going through the whole script for every frame, rendering all values for every frame, all values for the whole intro for every frame, and then only saving those that are relevant right now. So that's how it's so small. And it has all interpolation modes and output floats. A single small addition hack I did to Rocket last year, I think, was that we have this common issue in Rocket that you interpolate a variable in one scene, and then you want to do a sharp cut to the next scene, and then you will have this point where you actually have two values, and Rocket can't represent that. So you will have the movement stops in the last fraction of a second of one scene before you cut. Usually you will fix it brute forcing by running the script really fast, so it's a really small gap. It is actually quite easy to make a hack so you can move several keys into the same frame, same row. And then the replayer just has to support that. That will also mean that you can run your script really slow and have smaller values to compress. So how do we define it when doing the debug, the editor mode? I think this is quite a bit different from how normal Rocket is. I haven't looked into normal Rocket for 8 years or so. We have a list of labels, essentially. We have the number of bits we shift for the quantization for each channel. And then we have editor scales, because you can only use values at a certain scale in the editor. So, and you don't want to have scaling variables in your shader code that will take space. So we can, scale them up a bit or down just for the editor parts. And finally, we have the offset rows. You can see there are like one row before something usually is happening. That outputs a float array, and we just take that whole float array directly into the shader constant buffer and do some defines on the shader side, so it looks nicely in the shader. And what do we actually save in the 4K? Of course, the number of tracks and keys that is needed. Then we deduplicate the keys by having the active rows, the rows where something is actually happening. And then for each track, we point the keys to that array of rows. And both the active rows and the row keys are delta encoded bytes. Of course, you can always, if you have more than 256, you can always put in a dummy key. Then we have the mode, the interpolation mode. You can have 3 interpolation modes in normal Rockets, and for the replayer, it doesn't really take any space, so to have all 3. And the quantized values themselves. We can either output shorts or bytes, but in a 4K you really want to make it into bytes. It's 50 to 100 bytes on a normal one. For an 8K, yeah, you can go with the shorts if needed. Camera values especially usually is hard to get into a byte. And yeah, of course we have to save this quantization factor for every track. And some examples. This is from last year. So those numbers that are the active rows, the keys, what's the first one? The big one is, of course, the values, and the last one is quantization factors. Not sure what the 37 is. But it mostly says that we have 316 key value pairs in 413 bytes. Of course, the shader would be a lot larger if we had to do that in the shader part instead. Another example, more space for the music here, and smaller shader, more space for the CPU code also. We have 262 keys in 358 bytes. Fewer tracks, but more or less the same thing. Yeah, that's about it. That last link is Pestis intro from 2 years ago. He also did some rugged integration. I think it's too simple, but it's not bad at all, but I would prefer something a bit more complicated, but that's also something you could have a look at. Thank you.
Okay, so, thank you. So this is the set of slides again. And I have also put two links here. So if you're interested in 4K or 64K development, you have the two links that give you lots of resources about everything we talked about, or mesh generation and so on. And, for the people who are here, I think that there's a lunch organized by Zavie tomorrow, if you want to talk about it.
Oh yeah, we forgot to put the slide. Yeah. So tomorrow, 64K meetup at 1 p.m. in the bonfire area, and if you're like, show your I made a 64K card, and if you don't, you're still welcome. we will have food.
Okay, so thank you. I think we were a bit over time, so maybe we don't have time for questions. But if you want to ask questions to people here, I guess we can talk outside. And I think that's all. Thank you very much.